Let me solve diffraction grating problems number 6. The grating has 7,000 lines per centimeter. We want to know how many spectral orders can be seen when illuminated with white light. The white light will produce a large central spot. Okay, so there's a screen, there's a large central white spot there. Then there's some angle, some range of angles through which we have the first order of the visible light spectrum. So, it's a range here. And light, light. Lambda goes from 400 to 750 nanometers. And so keep that in mind as we figure out what we need to do here. Well, to figure out how many orders we would see, there's the first order. We would, by extension, theoretically, here would be the second order, possibly the third order, etc., etc. The condition that must be satisfied, the basic equation here, is d sine of theta is m lambda. But to determine how many full spectral orders you see, how many total sequences of all the visible light colors, the condition is that you can't have the angle be greater than 90 degrees. Here's, these angles can't go over 90 and actually be produced. All of a sudden, it would be behind the source of the light, which doesn't make any sense at all. So sine of theta is what we want to focus on. Sine of theta is equal to m lambda over d. And so the condition on sine of theta is that it has to be less than or equal to 1. So there's the condition. That's the condition that must be satisfied. Well, let's go ahead and solve for the first order situation. So in the first order, sine of theta 1 is equal to 1 lambda over d, which is equal to, to make, this has to be less than or equal to 1. So the worst case is where lambda is the biggest. So that means that's going to correspond to the red light at 750 nanometers. That's the furthest one away, the biggest angle. So violet, blue, green, etc., down to red. What we need to do now is solve for d. What is d? Well, 7,000 lines per centimeter corresponds to 1 over 7,000 centimeters per line. And that's equal to 1.43 times 10 to the negative 4. That's what that is. And so that's equal to 1.43 times, this is centimeters per line, 1.43 times 10 to the negative 6 meters per line. All right, so what we have here then is lambda is 750 nanometers, so times 10 to the negative 9, over d, this is d now, 1.43 times 10 to the negative 6, and that's equal to 0.52. So that looks good. Good. Yay! We have our first order. In other words, there's a solution for it. Let's see about the second order. In the second order, sine of theta 2 is equal to 2 lambda over d. But of course, that's just 2 times 0.52, which is 1.04. No! Sad face. You can't possibly have the sine of the angle be 1.04. So all we get is first order only. That's the answer. Certainly, we could get part of the second order, because this is real close. You know, we're real close to 1 by the time red, you know, lambda being the 750. It would work okay for the earlier colors, but by the time we get to red, this angle is actually, you know, this isn't shown correctly, basically, because it's, you know, the blue might be like this, and the red goes clear and back, which is impossible, of course. So that's the solution to that problem.